Evaporation. Evaporation, vaporization, two different words for the same things. That's a physical change where we're going from a liquid state to a gas state. So when water evaporates, it goes from liquid to a gas. How fast that occurs depends on a couple of things. It depends on the surface area. If you increase the surface area of the water, it will evaporate more quickly. So if you take a cup of water in a tall, skinny glass where the surface area exposed to the air is very small, or you take that same volume of water and you dump it on the floor where it spreads out and has big surface area, which one's going to evaporate faster? The one on the floor. It has a larger surface area. More surface area means faster evaporation. Increasing the temperature also speeds up evaporation. That's why you put a wet towel in the dryer and you turn the heat on, because it's going to dry faster than if you stick it in there and just leave it cold. The particles have more thermal energy and they're more able to escape. Decreasing the strength of the intermolecular forces also has an effect on the rate of vaporization. If you have very weak intermolecular forces, the particles are going to escape more quickly. Liquids that evaporate easily are called volatile. So volatile means that it evaporates quickly. Non-volatile does not vaporize quickly or easily. So how does how does intermolecular forces, the strength of intermolecular forces affect vaporization? Well, let's look at this illustration here. So here we have our little Mickey Mouse head water molecules, and they're moving around in here like water molecules do. And some of them at the surface might have enough energy, enough kinetic energy, that they can break away from the attractions to the other molecules. So this water has a temperature. The temperature is a measure of the average kinetic energy. But some of the molecules have high kinetic energy and some have low. And if you have a molecule with high kinetic energy that is moving at the surface, it can break loose and evaporate. If we heat this up, more particles are going to have enough energy and more will evaporate in a given amount of time. It'll evaporate more quickly. If we increase the surface area of this, then you have more particles at the surface, and so you have more opportunities for them to escape. The molecules down here at the bottom might have enough energy to evaporate, but if they're not at the surface, they can't go anywhere. So increasing surface area increases the rate of vaporization. Increasing the temperature increases it, and decreasing the strength of the intermolecular forces. You guys familiar with a game called Red Rover? I don't think they let kids play that in school anymore because somebody might get hurt. But it was a game, for those of you who don't know, where you get a bunch of kids in a line and you hold hands. And then across the field are some other kids, and you say, Red Rover, send Sally right over, right? And then Sally comes running towards this line of kids holding hands, and she's going to try to run fast enough to break through the hands, right? So the intermolecular forces are the water molecules at the surface holding hands. That's the Red Rover line. And in order for these guys, Sally's down here somewhere, in order for Sally to break through the line, first of all, she has to run at the line, right? You can't get through the line if you run the other way, or if you just stand there. You have to get to the surface. And she has to have enough speed to get through, enough energy to actually break through those arms, right? So let's think about two different groups of people playing Red Rover. You've got a group of kindergartners, and then you've got the O-line and D-line for the Fresno City College football team playing Red Rover. Which line is going to be harder to break through? The football players, right? Those guys are big. Have you seen them? They're big and strong. Kindergartners, that's going to be easy. You could probably just walk through them, right? What's the difference? It's the strength of how much they're holding on to each other, right? The strength of the intermolecular forces. So if we have very strong intermolecular forces here, it's going to be much harder for particles to get out and escape. the rate of evaporation is going to be low. If the intermolecular forces are very weak, lots of particles are going to get out. Does that make sense? Oh, good. Somebody remembered. Nodding means yes. We learned something. So evaporation and condensation. Condensation is the opposite. So here we have a graph. Scientists like to make graphs. So on the y-axis, the fraction of molecules, and on the x-axis, kinetic energy. If we look at a distribution of how many molecules have a given amount of kinetic energy, we're going to see it forms sort of a bell curve, but it's not symmetrical. So we have a variety of different kinetic energies, but most of them are kind of here in the middle, but there's a few that are high. If we increase the temperature of this liquid, the curve changes. Its peak moves to a higher kinetic energy, and it also spreads out. So the blue one has a lower average kinetic energy, and the red one has a higher average kinetic energy. If this line is the minimum energy that's needed to escape, to evaporate, we can look at the area under each of these curves as the number of molecules that has enough energy to escape. So when we increase the temperature, we increase the number of molecules that has enough energy to escape, and the evaporation occurs faster. Condensation is the opposite of evaporation. It's going from a gas to a liquid. If you have a closed container with an empty space and a liquid, you're going to get an equilibrium, a dynamic equilibrium occurring between evaporation and condensation. So you're going to have a liquid and a gas present. The gas above the liquid is going to exert a pressure, because all gases exert pressures, and that vapor pressure, we call it a partial pressure of the vapor that's in dynamic equilibrium with its liquid. That didn't go very well. This will be better. I like this better. Okay, so let's imagine here we have an Erlenmeyer flask with a stopper in it, and we have some water in it, and there's a lot of just empty space here. So this water is going to begin to evaporate, because that's what water does. At pretty much any temperature, at least a couple molecules are going to have enough energy to evaporate. So we're going to get some evaporation. At this point, there's no condensation, because in order to have condensation, there has to be water molecules in the gas state. There aren't any. So we've just got evaporation. As more molecules evaporate and we get more gas molecules here, then we're going to start to increase the rate of condensation. Because when this molecule escapes from the liquid, it does what gases do, and it travels in a straight line till it bumps into something. And so it travels around and it bumps in, and eventually it's going to bump into the surface of the water and get stuck. So you've got things coming out of the water, and then you've got things going back in. And eventually you're going to get to a dynamic equilibrium where the rate of evaporation is equal to the rate of condensation. So you have water vapor up here. That water vapor has a pressure. We call it the vapor pressure, and it depends on the temperature of the liquid. Any questions? Vapor pressure will increase if we increase the temperature. We did an experiment in lab where we had to look up the vapor pressure of water. It just depends on the temperature of the water. Let's go back to this for a minute. So if I heat up this water, what does that do to the rate of evaporation? It's going to increase it. That's the Red Rover people running faster. You're more likely to get through the Red Rover line if you run faster. So that's going to increase the rate of evaporation. That's going to cause there to be more gas molecules than there were at the lower temperature. Gas molecules, more gas molecules means more pressure. The pressure goes up as the temperature rises. The other thing that affects vapor pressure is the strength of the intermolecular forces. So if you have a liquid with low intermolecular forces and a liquid with high intermolecular forces at the same temperature, the one with low intermolecular forces will have a higher vapor pressure because more of its particles are able to escape than the high intermolecular force one. The surface area doesn't affect the vapor pressure. So if we look at this one that's in equilibrium, if we increase the surface area, if we make it a wider Erlenmeyer flask so this can spread out, that's going to affect the rate of evaporation and the rate of condensation equally. Because if you have a larger area, then more of these are going to get trapped again. So increasing the surface area doesn't affect the vapor pressure. It's the temperature and the strength of the intermolecular forces. Any questions? Boiling. So the boiling point is the temperature at which the vapor pressure of a liquid is equal to the pressure above it. So the vapor pressure increases as the temperature increases. If you just keep heating it up and heating it up and heating it up, eventually you'll get to a vapor pressure that equals atmospheric pressure. When that happens, the molecules within the interior of the liquid have enough energy to escape into the gas state. And they will do that and make little bubbles. These little bubbles of vapor then are much less dense than the water around them, and so they'll come to the surface and break, and those particles will escape. So the thermal energy is enough that they can escape even deep inside. The cool thing about that is you can make water boil at room temperature. You believe that? All you have to do is lower the pressure above the water. So you get a big vacuum pump, and you pump the air out of this container, and you reduce the pressure in the container until it gets down to the vapor pressure of water at room temperature, which is about 25 millimeters of mercury. It's pretty low, but you can make water boil at room temperature. So once you get to the boiling point of a liquid, if you heat it more, it's only going to cause it to boil more rapidly. It's not going to cause the temperature of the liquid to increase. This is something that's not intuitive, and it has some impact on your daily life. If you're cooking spaghetti and you're in a hurry, right? You get the water boiling, you stick the spaghetti in there. If you heat the boiling water longer, does it get hotter? It doesn't. It gets to the boiling point of water, 100 degrees Celsius, and no matter how much heat you put into it, it's going to stay at 100 degrees Celsius until it has all converted to steam. Think about that. That should seem weird. So if we, again with the graphs, here's the temperature of the water. We're starting out at 20 degrees, and here we're adding heat. We add heat and the temperature goes up, and we add heat and the temperature goes up. And it goes up linearly. It's very nice. And then when we get to 100 degrees, the water begins to boil. And we're still adding heat, add more and more heat. The temperature doesn't change until all the water has boiled away. Once all the water in your spaghetti pot has boiled away, the temperature in there is going to go up fast. Until all the water's gone, though, it'll stay at 100 degrees. Yes?
Does steam have like a boiling point with a certain, I guess, tip towards max?
Does steam have a maximum temperature it can get to? Not that I know of. No. So once it all converts to steam and you add heat, the temperature of the steam will just continue to go up. Okay, so does anybody wonder why that is? How does that work? Well, evaporation is endothermic. The system's going to absorb heat because energy is needed to break molecules away from the liquid. You think about that. How do you get water to boil? You heat it up, right? You put heat into it. It's endothermic. And our bodies use this process to cool us down. We call it sweating. So you sweat and you've got water on your skin. Which particles are the ones that actually make it into the gas state and fly away? Is it the high energy ones or the low energy ones? It's the high energy ones. So you've got the high energy particles leaving. What does that do to the average energy of the particles that are left when all the high ones go away? The average goes down. So as water evaporates, it has a cooling effect because it's taking energy away from your skin. Your skin puts energy into the water, and then the higher energy water molecules evaporate away, and that cools us. High humidity slows that down. I grew up in the Midwest where 90 degrees is really, really uncomfortable because it might also be 90% humidity. And when the humidity is high, your sweat doesn't evaporate. You just go around wet all the time, and it doesn't do any good. Here, where the humidity is low, you sweat, and there's a little tiny breeze, and it evaporates, and you're like, oh, that feels so good. It cooled me off. When the air has a high water content, it's harder for it to take on more water molecules, and so water doesn't evaporate as quickly. Condensation, being the opposite process of evaporation, is an exothermic process. And this is another thing that's kind of counterintuitive. So heat is released when a gas condenses to a liquid. You may have experienced this. Steam will give you a much worse burn than water will. Because when steam hits your skin, and your skin is cooler than the boiling point of the water, the steam condenses, and just the fact that it's condensing releases a lot of energy, in the same way that something evaporating absorbs energy. And this whole condensation being exothermic, evaporation being endothermic, is how water has a moderating effect on our climate. It keeps the temperature from varying as much. At night, when it's humid, the water condenses out of the air, and as it condenses, it releases energy. Did you know that freezing an ice cube is an exothermic process? That sounds weird, doesn't it? Because we think of exothermic as something giving off heat. But do you know what the condenser and the compressor on your freezer are doing? They're pulling heat, they're pulling energy out of the freezer. The way you get water to freeze into a solid is by pulling the heat out of it. The opposite makes more sense. How do you get an ice cube to melt? Well, you warm it up, right? You hold it in your hands, and you feel the heat from your hands going into the ice cube. Your hands get cold. But the opposite doesn't happen spontaneously, but we can make it happen. Okay, heat of vaporization. Of course, if there's heat being transferred, we're going to want to quantify that. We're going to measure it. So we've seen delta H before. We talked about heat of reaction. The heat of vaporization is the amount of heat needed to vaporize 1 mole of liquid. So if we look at this very simple chemical equation here, we've got water in a liquid state going to water in the gas state. There's energy involved in that. Going from a liquid to a gas requires that we put energy in. It's endothermic. So delta H for that reaction is a positive number. So endothermic means heat coming in. Money coming into my wallet is a positive experience for me. right? So this is a positive delta H. If it requires 40.7 kilojoules to vaporize 1 mole of water, then it's also going to release 40.7 kilojoules of energy when 1 mole of water condenses. Otherwise, we could generate energy by just heating and cooling things. So the opposite, water in the gas state going to water in the liquid state, condensation, the number's the same, the sign is different. Because this is exothermic, heat is exiting, and so this is a negative number, because I feel negative when money goes out of my wallet. Any questions? We can use the heat of vaporization to figure out how much heat energy is needed to vaporize a given amount of liquid. I can't answer the question of why would we want to do that, but maybe you want to do it to pass an exam. That might be a good reason. So heats of vaporization are another thing that you don't need to memorize. If you need it on an exam, it will be given to you either in a table or within the problem. But on homework, you might have to go look it up somewhere. And here's a table in your book that's useful. So here's the heat of vaporization at the boiling point of the liquid and at room temperature. And it kind of makes sense that it requires less energy to boil something at its boiling point than it does at room temperature. And then here are listed the normal boiling points. So here's a couple of four different liquids: water, rubbing alcohol, acetone, that's the thing in nail polish remover, and then diethyl ether. Well, how would we calculate this? Calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. The heat of vaporization is 40.7 kilojoules per mole. This basically comes down to a unit conversion problem. It's just dimensional analysis. Well, we've been given two numbers, right? 2.58 and 40.7. Let's look at the units. This is kilograms. This is kilojoules per mole. We're going to do dimensional analysis. We have to start with one number. And so we're going to look at the units. Simple unit, just a single unit, or a compound unit. This is per. This is the conversion factor. The one with the single unit is the thing we're starting with. So we're starting with 2.58 kilograms. And what does it ask us to find? What unit? Kilojoules. So we want to find kilojoules over here. Again, we figure out where we are and where we're trying to go, and then we figure out how to get from the starting point to the ending point. Well, we've got this right here, kilojoules per mole. This is the relationship between kilojoules and mole for this particular situation. So if I had moles of water, I could get to kilojoules by using this heat of vaporization. And then I need to get from kilograms of water to moles of water. Well, what have we done a lot of? Grams to moles, right? So if I had grams of water, I could get to moles of water using the molar mass of water. Can I go from kilograms to grams? The answer should be yes. So there we have a path. Once we've got the path written out, then we can write out the equation. We have three arrows. We're going to have three conversion factors, three fractions. So 2.58 kilograms times in a line, times in a line, times in a line. And these are the units: kilograms to grams to moles to kilojoules. Kilograms to grams to moles to kilojoules. And then we put the units in the bottom so they cancel out. We want moles to cancel. We want grams to cancel. And we want kilograms to cancel. Well, this is the one that's given to us, 40.7 kilojoules per mole. Well, here I have kilojoules over moles. So 40.7 goes with the kilojoules. And if I really need a number down there, it would be 1. How do we convert grams to kilograms, or vice versa? We need to know what kilo stands for, right? Kilo stands for 1,000. I don't want to put 1,000 with kilo, though. I want to put 1,000 on the other side. So 10 to the 3 is what kilo means. So 1 kilogram is 1 times 10 to the 3rd grams. This is the molar mass. I'm not going to take the time to calculate that. 18.06 grams per mole is 2 hydrogens plus an oxygen. And then we just do the math. 2.58 times 1 EE3 divided by 18.016 times 40.7. How many sig figs should that have? 3. So that's going to be 5.83 times 10 to the 3rd kilojoules. Any questions?